Summer 1943, Wright-Patterson Air Force Base, Ohio. A silver P-47 Thunderbolt screamed through the sky at an altitude of 30,000 feet. In the cockpit, test pilot Major Robert Davidson pushed the control stick forward, sending the 7-ton fighter into a near-vertical dive. The airspeed indicator swept past 450 miles per hour, then 500 miles per hour, approaching speeds no American fighter had safely achieved. At 550 miles per hour, the massive aircraft began to shudder violently as aerodynamic forces threatened to tear it apart. Yet the P-47 continued its plunge, the airframe holding together when any other fighter would have disintegrated. When Davidson finally pulled out of the dive at 15,000 feet, subjecting himself to crushing G-forces, the P-47's wings remained firmly attached to the fuselage. The impossible had just been proven possible. What made this achievement extraordinary was that 2 years earlier, metallurgists had declared that no aluminum alloy could withstand such stresses. The P-47's ability to dive at these speeds and survive was due to one woman's revolutionary metal alloy that defied conventional wisdom in metallurgical science. That alloy would give American pilots a crucial advantage in dogfights against German fighters, ultimately saving hundreds of lives and helping turn the tide of air combat in World War II. This is the story of how one metallurgist's insistence on pushing the boundaries of materials science transformed aerial warfare and contributed materially to Allied victory. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The journey to that breakthrough moment in Ohio began in October 1941 when Dr. Elizabeth Holloway walked through the doors of Republic Aviation's research laboratory in Farmingdale, Long Island, as their new head of materials science. Born on the 17th of March 1906 in Brockton, Massachusetts, Holloway had earned her doctorate in metallurgical engineering from MIT, one of only 3 women to do so, in the 1932nd, and had made her reputation developing high-strength aluminum alloys for naval applications at the Philadelphia Naval Shipyard. Her expertise in metal fatigue and stress resistance would prove invaluable at a pivotal moment in aviation history. War had engulfed Europe. France had fallen to Nazi Germany the previous year. Britain stood alone against the Third Reich, enduring the Blitz, while the Royal Air Force fought desperately in the Battle of Britain. Though America remained officially neutral, military involvement seemed inevitable to anyone paying attention. President Roosevelt had begun the military build-up that would accelerate dramatically over the next year. The Army Air Corps was scrambling to develop fighter aircraft that could match or exceed the performance of the German Luftwaffe's Messerschmitt Bf 109 and the newer Focke-Wulf FW-190, which was proving superior to anything the Allies had in the air. Among the many challenges American aircraft designers faced, structural integrity at high speeds ranked among the most critical. Modern air warfare required fighter aircraft capable of extraordinary performance, tight turns, high-speed dives, and rapid acceleration, all while maintaining control and structural integrity. Fighter pilots needed aircraft that could dive away from danger when outnumbered, accelerate quickly to gain advantageous position, and withstand the tremendous forces generated during combat maneuvers. Reconnaissance planes needed to outrun enemy interceptors. Bombers needed escort fighters that could stay with them throughout their missions and protect them from enemy fighters. Commanders needed aircraft that wouldn't break apart under the stresses of combat maneuvering, leaving pilots doomed to death or capture. But the aircraft available in 1941 were woefully inadequate for these demands. The Army Air Corps had experimented with various fighter designs, but these early efforts had shown alarming tendencies to develop structural failures during high-speed dives and tight maneuvers. The P-40 Warhawk and P-39 Airacobra, America's frontline fighters in 1941, both suffered from performance limitations that left them vulnerable against German and Japanese fighters. They used conventional aluminum alloys that simply couldn't handle the stresses of modern air combat. At high speeds, their control surfaces became dangerously stiff. Wings flexed and sometimes developed fatal cracks. Airframes twisted and buckled. The materials simply weren't up to the task. These limitations meant American pilots entered combat with a severe disadvantage. They couldn't dive away from superior enemy aircraft. They couldn't execute the high-speed maneuvers needed to gain advantage in a dogfight. They were, in effect, fighting with one hand tied behind their back. Many aviation engineers had grown deeply skeptical about the possibility of creating a fighter capable of sustained high-speed dives exceeding 500 miles per hour. The laws of physics and the limitations of existing materials seemed to present an insurmountable barrier. Republic Aviation had achieved some success with their P-43 Lancer, but it was clear that a more robust, powerful fighter was needed for the coming conflict. Alexander Kartveli, Republic's chief designer, had been working on a successor that would eventually become the P-47 Thunderbolt. The massive fighter, powered by a Pratt & Whitney R2800 double Wasp engine with a supercharger, promised to be one of the most powerful aircraft ever built. But its size and weight created unprecedented structural challenges. How could they build an airframe strong enough to handle the immense power without becoming too heavy to maneuver effectively? The conventional wisdom held that they would need to compromise either on speed or on structural integrity. There simply wasn't an aluminum alloy available that could provide both the strength and the weight characteristics needed. It was into this environment of seemingly insurmountable technical challenges that Elizabeth Holloway stepped. Within her first week at Republic, she attended a design review meeting where Kartveli and his engineering team were discussing the structural limitations of the P-47 prototype. The atmosphere was tense, with engineers debating how to address the problem of wing failure during high-speed dives. The leading metallurgist, Dr. Harold Fitzgerald, explained that they had reached the limits of what was possible with aluminum alloys. "The 2024 alloy we're using is the strongest available," he stated flatly. "If we make the wings any thicker to increase strength, we'll add too much weight and kill performance. If we keep them thin, they'll fail at speeds above 450 miles per hour in a dive. There's no way around it, it's basic materials science." Holloway, who had been quietly listening, spoke up. "I believe there is a way around it," she said, her voice clear and confident in the room full of male engineers. "The problem isn't with aluminum itself, but with our approach to alloying and heat treatment. I've been working on a new technique that could increase tensile strength by nearly 40% while actually reducing weight." The room fell silent. Fitzgerald looked skeptical. "That's impossible," he said. "We've tried every combination of copper, magnesium, and manganese. The metallurgical limitations are well established. Not if you introduce scandium and precisely controlled cryogenic treatment," Holloway countered. She went on to explain that her research at the naval shipyard had shown that trace amounts of scandium, a rare earth element, combined with a precisely controlled cooling process using liquid nitrogen, created a fundamentally different microstructure in the aluminum alloy. This new microstructure distributed stress more evenly throughout the material, preventing the formation and propagation of microfractures that led to catastrophic failure. Her proposal was met with skepticism bordering on derision. Scandium was rare and expensive. Cryogenic treatment of aluminum alloys was considered exotic and impractical for mass production. The manufacturing challenges seemed insurmountable, but Holloway was unfazed. She had brought her research notes and preliminary test results, which showed promising strength to weight characteristics in laboratory samples. Alexander Kartveli, unlike some of his engineers, recognized the potential importance of Holloway's proposal. If she was right, if her alloy could deliver even half of the performance improvement, she claimed it would transform the P-47 from a powerful but limited fighter into something revolutionary. He gave her 2 weeks to produce a demonstration sample that could be subjected to stress testing. What followed was a period of intense work. Holloway barely left the laboratory, sleeping on a cot in her office and working around the clock. She assembled a small team of like-minded metallurgists who believed in her approach. James Chen, a brilliant crystallography expert who had studied in China before coming to America. Maria Diaz, a chemical engineer with expertise in rare earth elements, and Robert Weissman, a manufacturing specialist who could translate laboratory success into production processes. The challenge they faced was enormous. They needed to source scarce scandium, develop precise thermal control methods for the cryogenic treatment, and create test samples that could be evaluated according to the rigorous standards required for aircraft components. All of this while facing quiet but persistent skepticism from many of their colleagues, who believed they were wasting valuable time and resources on a metallurgical wild goose chase. 14 days later, Holloway and her team presented their first test samples to Kartveli and a group of Republic's senior engineers. The samples were subjected to stress tests that simulated the forces a dive bomber wing would experience at speeds exceeding 500 miles per hour. When the conventional 2024 alloy sample failed catastrophically at forces equivalent to a 465 miles per hour dive, Holloway's scandium-infused alloy showed no signs of stress or deformation. The engineers were stunned. They insisted on repeating the tests, suspecting some kind of error or manipulation. The results were the same. Holloway's alloy, which she had designated R41S, Republic 41 scandium, demonstrated strength properties that exceeded anything previously achieved with aluminum, while maintaining weight characteristics that made it practical for aircraft construction. Kartveli immediately recognized the implications. With this alloy, he told the assembled team, we can build a fighter that can dive faster than anything in the sky, pull out without structural failure, and still be maneuverable enough for dogfighting. This changes everything. But enthusiasm in the laboratory didn't translate to immediate acceptance by Republic's production managers or by the Army Air Corps procurement officers, who would have to approve any change in materials for the P-47. When Holloway and Kartveli presented their findings to Colonel Edward Clark, the Air Corps officer overseeing fighter development, his response was immediate and negative. We're already tooling up production lines based on standard alloys, he said. Changing materials now would cause unacceptable delays, and this scandium element, where would we even get it in the quantities needed for mass production? No, this is an interesting laboratory curiosity, but it's not practical for wartime production. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. Holloway refused to accept this dismissal. She had not spent 2 sleepless weeks creating a laboratory curiosity. She had developed a material that could save pilots' lives and give American fighters a decisive advantage in air combat. She requested a meeting with General Henry Hap Arnold, Commanding General of the Army Air Forces, who was visiting Republic's facilities the following week. The meeting was brief but pivotal. General Arnold, unlike Colonel Clark, immediately grasped the strategic implications of Holloway's alloy. A veteran pilot himself, he had seen too many aircraft failures and lost too many pilots to structural limitations. When Holloway explained that her alloy could allow the P-47 to dive at speeds approaching 550 miles per hour, far faster than any enemy fighter could follow, and then pull out safely, Arnold made an on-the-spot decision. Colonel Clark, he said to the procurement officer who had accompanied him, I want a test program for this alloy immediately. If Dr. Holloway's claims hold up in actual flight testing, we'll find the scandium and whatever else is needed. The advantage this could give our boys in combat is too important to ignore. Made in a matter of minutes, set in motion a program that would eventually transform the P-47 Thunderbolt into the most structurally robust fighter aircraft of World War II. But the path from laboratory sample to combat aircraft was far from smooth. The first challenge was securing enough scandium, an element so rare it had been discovered only 60 years earlier and had no established mining or refining industry. Holloway and her team worked with the War Production Board to identify potential sources. They discovered that scandium could be extracted as a byproduct from uranium mining operations in Colorado and from certain tungsten ores in Nevada. It wasn't abundant, but there was enough to support limited production if extraction methods could be developed quickly. Maria Diaz took on this challenge, working with mining engineers to develop efficient extraction processes. Within 3 months, they had established a small but steady supply chain that could provide the modest amounts of scandium needed. Only about 0.5% by weight was required to achieve the dramatic strength improvements in the alloy. Meanwhile, Robert Weissman tackled the manufacturing challenges. The cryogenic treatment process that Holloway had developed in the laboratory needed to be scaled up for production while maintaining precise temperature control. Working with refrigeration engineers from Westinghouse, Weissman designed a production system that could process wing spars and other critical components in batches, immersing them in liquid nitrogen baths at precisely controlled rates to achieve the microstructural changes needed. By spring of 1942, they had produced enough of the R-41S alloy to build a complete set of wings and critical structural components for a P-47 prototype. The aircraft, designated XP-47E, was essentially identical to the standard P-47, except for its specially alloyed components. Test pilot Major Robert Davidson was selected to put the aircraft through its paces at Wright Field. The initial flight tests were conservative, gradually expanding the flight envelope to ensure the new alloy performed as expected under normal conditions. The XP-47E handled identically to the standard P-47, which was a good sign the alloy wasn't changing the aircraft's basic flight characteristics. But the real test would come when Davidson pushed the aircraft to its limits in high-speed dives. On the 12th of June 1942, Davidson took the XP-47E to 30,000 feet and prepared for a maximum speed dive test. Engineers on the ground, including Holloway and her team, monitored radio transmissions with growing tension. The standard P-47 had demonstrated dive speeds up to about 470 miles per hour before pilots reported severe buffeting and control difficulties. Anything beyond that was considered potentially catastrophic. "Beginning dive now," Davidson's voice crackled over the radio, "passing through 450 miles per hour, 475, 500. There was a pause. The ground crew held their breath. 525, aircraft handling smoothly, some buffeting but controls still responsive. 550 miles per hour. When Davidson pulled out of the dive and returned to Wright Field, his debriefing electrified the test program. The XP-47E had not only survived a 550 miles per hour dive, but had remained controllable throughout. Subsequent instrumented tests confirmed that the R-41S alloy components showed minimal stress and no signs of fatigue or deformation after repeated high-speed dives. The implications were enormous. The P-47, already a formidable fighter due to its heavy armament and powerful engine, would now be able to employ tactics that no enemy fighter could match. A P-47 pilot, if outmatched in a dogfight, could simply push the nose down and dive away at speeds that would tear apart any pursuing Messerschmitt or Focke-Wulf. The same capability would allow P-47 seconds to attack from above with devastating high-speed passes that left enemy aircraft unable to pursue. General Arnold, upon receiving the test results, immediately authorized full production implementation of the R-41S alloy for all critical P-47 components. This decision represented a significant production challenge for Republic, but Arnold made it clear that the performance advantage was worth whatever retooling and supply chain adjustments were necessary. By December 1942, the first production P-47 seconds with Holloway's special alloy were rolling off the assembly line. These aircraft, while visually indistinguishable from earlier models, represented a quantum leap in structural integrity and performance capabilities. As they prepared to ship overseas to combat units, Holloway felt a profound sense of accomplishment, tinged with the solemn knowledge that her work would now be tested not in laboratories or test flights, but in the life-and-death struggle of aerial combat. Looking at the gleaming fighters awaiting shipment, she turned to James Chen and said quietly, "We've done what they said was impossible. Now, let's hope it makes a difference where it matters most." January 1943, a fighter airfield in England. A cold winter rain pelted the aluminum skin of the P-47 Thunderbolts lined up on the tarmac, their massive frames dwarfing the British Spitfires parked nearby. Captain James Walton of the 56th Fighter Group stared skeptically at his new mount. Having flown P-42s in North Africa, he was accustomed to sleek, nimble fighters, not this behemoth the pilots had already nicknamed the Jug for its bulky, jug-like fuselage. "She looks like she'd drop like a brick," he commented to the crew chief, checking the massive R2800 engine. "Just wait till you get her upstairs," the mechanic replied with a knowing smile. "These birds have a special secret, something about a new metal in the wings. Word is they can outdive anything the Germans have." Walton remained unconvinced until 2 days later, when he found himself at 28,000 feet over the English Channel, escorting B-17 seconds toward occupied France. The encounter with Luftwaffe fighters was sudden 12 Fokker-Wulf, 190 seconds, slashing through the bomber formation from above. As the furball of twisting, turning aircraft developed, Walton found himself outmaneuvered by a skilled German pilot who clung to his tail despite his best efforts to shake him. With cannon shells streaming past his canopy, Walton did the only thing he could, pushed his stick forward and dove straight down, the massive Thunderbolt accelerating with astonishing speed. His airspeed indicator passed 500 miles per hour as the English Channel rushed up to meet him. In his rearview mirror, he saw the pursuing Fokker-Wulf attempt to follow, then abruptly pull back as its wings began to shudder violently. The German fighter broke off, unable to match the P-47's dive without risking structural failure. When Walton landed back at base, his hands still shaking from the adrenaline, he sought out the group's technical officer. "What's really in these things?" he demanded. "I hit speeds that should have torn the wings right off," but she handled like a dream. The P-47 seconds that saved Walton's life that day over the Channel were among the first combat-deployed fighters featuring Elizabeth Holloway's revolutionary R-41S alloy. The special secret that the crew chief had mentioned was now proving its worth not in laboratory tests, but in the life-or-death struggle for air superiority over Europe. That dive capability would soon become the P-47 pilot's signature tactic and a critical advantage in the air war. Meanwhile, back in the United States, Holloway and her team weren't resting on their success. They understood that getting the R-41S alloy into production was just the first step. Now they faced the challenge of scaling up manufacturing to meet the enormous demand, as the Army Air Forces ordered increasing numbers of P-47 seconds for combat in both European and Pacific theaters. The scandium supply chain remained a significant bottleneck. Maria Diaz was working with mining operations across the American West to increase production of the rare element, but demand continued to outstrip supply. In February 1943, Holloway received an urgent call from the War Production Board. A German U-boat had sunk a cargo ship, carrying a substantial portion of that month's scandium supply from processing facilities in Colorado to Republic's factory in Farmingdale. This potential crisis required an immediate solution. During an emergency meeting with Republic executives and Army Air Forces representatives, Holloway proposed a technical modification. "We've been running tests with varying scandium concentrations," she explained. "We found that by adjusting the cryogenic treatment protocol, we can achieve almost identical structural properties with 30% less scandium per unit." Colonel Clark, who had initially opposed the R-41S program but now recognized its value, pressed for details. "Will that compromise the dive performance at all? We're getting reports from the 8th Air Force that the dive capability is saving pilots' lives daily." "No compromise on performance," Holloway assured him. "Just a more efficient use of the scandium we have available." The microstructural changes occur at a molecular level, and we've found we can achieve the same crystalline matrix with more precise temperature control during treatment. The modified process was approved and implemented within weeks, allowing production to continue without interruption despite the scandium shortfall. This kind of agile problem-solving became a hallmark of Holloway's team as they worked to support the expanding P-47 production lines. By spring 1943, P-47 seconds with the R-41S alloy were seeing widespread combat across the European theatre. Republic's factory was producing the fighters at an increasing rate, with production eventually reaching nearly 100 aircraft per month. Each one incorporated Holloway's special alloy in its wings, tail assembly, and other critical structural components. The impact on combat operations was becoming increasingly apparent. Major General William Kepner, commanding the 8 Fighter Command, reported directly to General Arnold, "The P-47's ability to dive away from trouble has completely changed our tactical approach. Pilots report regularly that when outmatched by superior numbers or position, they can dive to safety at speeds enemy fighters cannot match without breaking apart. This has dramatically reduced our loss rates and increased pilot confidence." What made this achievement even more remarkable was that German metallurgists were struggling with similar structural challenges, but had not found an equivalent solution. Intelligence reports from captured Luftwaffe technical documents revealed that German engineers had experimented with various aluminum alloys, but had not discovered the scandium cryogenic treatment approach that Holloway had pioneered. The Focke-Wulf 190, Germany's premier fighter in 1943, was limited to maximum dive speeds of approximately 460 miles per hour before experiencing dangerous control, buffeting, and structural stress. The Messerschmitt Bf 109G faced even more severe limitations, with documented cases of wing failure at speeds above 450 miles per hour in steep dives. This performance gap gave American pilots a critical escape mechanism when tactically disadvantaged and allowed aggressive diving attacks that enemy fighters couldn't follow. Back at Republic's research laboratory, James Chen was analyzing captured fragments of German fighter aircraft, comparing their metallurgical properties to the R41S alloy. "The Germans are using a conventional aluminum-zinc alloy with excellent general properties," he reported to Holloway, "but they've hit the same wall we faced before your scandium innovation. Their alloys simply cannot handle the stresses of high-speed dives without increasing weight to impractical levels." This confirmation that the Allies had achieved a genuine technological advantage was gratifying, but Holloway remained focused on further improvements. Reports from maintenance crews in England indicated that while the R41S components were performing exceptionally well in combat, they showed higher than expected fatigue rates during routine inspections. Aircraft that had seen extensive combat were developing microscopic stress fractures at key structural junctions, not enough to cause immediate failure, but concerning for long-term durability. Robert Weissman took the lead on addressing this issue, working with Republic's structural engineers to identify the specific stress points where fatigue was appearing. They discovered that the junction between the main wing spar and the fuselage attachment points was experiencing complex multi-directional forces during high-G maneuvers following high-speed dives. The R41S alloy handled pure tensile stress brilliantly, but was less effective against this complex torsional loading. This led to the development of R41ST Republic 41 scandium torsion, a modified version of the alloy with a slightly different heat treatment protocol that created a more isotropic uniform in all directions, microstructure. By April 1943, this improved alloy was incorporated into production, further enhancing the P-47's structural integrity during the most demanding combat maneuvers. As production of the R41S and R41ST alloys expanded, Elizabeth Holloway faced an unexpected challenge from an entirely different quarter. The success of her metallurgical innovation had attracted attention from other aircraft manufacturers and military branches. The Navy's Bureau of Aeronautics requested that Holloway consult on applying her alloy technology to carrier-based aircraft, which faced their own extreme structural challenges during arrested landings on heaving carrier decks. Simultaneously, Boeing was interested in incorporating the alloy into critical components of their B-17 Flying Fortress bombers, particularly in the tail assembly, which was vulnerable to structural failure during the extreme evasive maneuvers pilots used to avoid flak and fighters. These requests created a difficult decision for the War Production Board, which was responsible for allocating critical resources and expertise. Holloway could not be everywhere at once, and the scandium supply chain, though improving, remained limited. After consultation with General Arnold and other senior military leaders, a compromise was reached. Holloway would remain focused primarily on the P-47 program, which was proving its combat value daily, but would dedicate 1 day per week to consulting with Navy metallurgists to adapt the alloy technology for naval aircraft. The Navy collaboration led to a modified version of the alloy, designated N41S, Navy 41 scandium, which was optimized for the unique stress patterns of carrier operations. By late 1943, this variant was being incorporated into the wing fold mechanisms of the new F-6F Hellcat fighters, addressing a critical failure point that had plagued earlier carrier aircraft. Meanwhile, James Chen took the lead on the Boeing collaboration, adapting the alloy for bomber applications where weight savings was even more critical than in fighters. A bomber-specific variant, B-41S, used slightly less scandium but incorporated more magnesium to further reduce weight, while maintaining adequate structural integrity for the less extreme stress environments bombers typically experienced. This dissemination of Holloway's core innovation across multiple aircraft programs amplified its impact on the Allied air campaign, creating a family of related high-performance alloys that addressed specific challenges across different aircraft types. The common thread running through all these variants was the scandium cryogenic treatment approach that Holloway had pioneered against considerable institutional skepticism. June 1943 brought Elizabeth Holloway to Wright Field for a demonstration that would showcase the full potential of her metallurgical breakthrough. The Air Technical Service Command had arranged a special flight test comparing the dive performance of a P-47 Thunderbolt equipped with her R41 ST alloy against a captured Focke-Wulf 190A, Germany's premier fighter. The test would be conducted under carefully controlled conditions, with instrumentation to measure airframe stress, control forces, and maximum sustainable dive speeds. Major Robert Davidson, who had conducted the original high-speed tests of the XP-47E prototype, would fly the P-47. Captain Erich Schilling, an experienced test pilot with extensive German aircraft experience, would fly the captured FW-190. The goal was to quantify exactly how much of an advantage the R41 ST alloy provided in maximum dive speed and structural integrity. A crowd of military officials and engineers gathered for the demonstration, including General Arnold, who had made a special trip to witness the comparative test. Holloway stood next to Alexander Kartveli, Republic's chief designer, as the two aircraft climbed to 30,000 feet, their contrails visible against the clear blue Ohio sky. At a signal from the test director, both aircraft rolled inverted and pulled into near-vertical dives. Initially, they descended together, but as their speeds passed 400 miles per hour, differences became apparent. The P-47, its massive frame slicing through the air, continued to accelerate smoothly. The W-190, though smaller and more streamlined in appearance, began to exhibit visible buffeting, its control surfaces fluttering as aerodynamic forces built up. At 450 miles per hour, Captain Schilling in the FW-190 began his pullout, radioing that the controls were becoming dangerously stiff and the airframe was shuddering violently. Davidson's P-47 continued its plunge, still accelerating, still stable. His voice came calmly over the radio as he passed 500 miles per hour, then 525, then 550, before finally executing a smooth pullout that subjected the airframe to over 5 G of force without any sign of structural distress. The instrumentation told the story in precise technical detail, but the visual demonstration had made the point more powerfully than any data could. The P-47, thanks to Holloway's alloy, could safely operate in speed regimes that would tear apart the best German fighter. This wasn't a minor technical edge. It was a decisive combat advantage that was saving lives daily over occupied Europe. General Arnold approached Holloway after the demonstration, shaking her hand firmly. "Dr. Holloway, when we first discussed your alloy last year, I thought we might gain a small technical advantage. What you've given us is far more. You've given our boys a way home when they're in trouble up there. That's beyond value." The validation from such a senior officer was gratifying, But Holloway was more moved by a letter she received the following week from Captain James Walton, the P-47 pilot who had escaped from a Fokker-Wulf by diving away at high speed over the English Channel. Walton had no idea who Holloway was or what role she had played in developing the alloy that had saved his life, but his squadron commander had forwarded his combat report to Republic Aviation as an example of the P-47's superior dive performance. "Whoever designed this aircraft's ability to dive so fast deserves a medal," Walton had written. "I'm alive today because my P-47 could do something the German pilot's aircraft simply couldn't attempt without coming apart. There were no clever tactics involved, just the raw structural integrity of this magnificent machine." That letter, more than any official recognition, confirmed for Holloway the real-world impact of her work. She had it framed and hung on the wall of her laboratory, a daily reminder of why the endless hours, the technical challenges, and the institutional resistance had all been worthwhile. By autumn 1943, the R41ST alloy was being incorporated not just into the P-47, but into modified versions for the P-51 Mustang's wing structure as well. While the Mustang had excellent overall performance, its original wing design had shown vulnerability to failure during extreme high-speed maneuvers. The incorporation of Holloway's alloy technology addressed this limitation, making the P-51 not only fast and long-ranged, but also structurally robust enough for the most demanding combat situations. This cross-platform application represented the kind of synergy that was becoming increasingly important as the Allied air campaign intensified. Each aircraft had its strengths, the P-47's ruggedness and firepower, the P-51's range and speed, but all benefited from the structural integrity that Holloway's metallurgical breakthrough provided. American fighter pilots could push their machines to limits that enemy pilots simply couldn't match without risking catastrophic structural failure. In October 1943, Elizabeth Holloway received a confidential intelligence report that confirmed the strategic impact of her work. Luftwaffe documents captured during the Allied invasion of Italy revealed that German aircraft designers were desperately trying to understand why American fighters, particularly the P-47, could sustain dive speeds that tore their own aircraft apart. They had concluded that the Americans must be using some form of advanced aluminum alloy, but their analysis of downed P-47 components had failed to identify the scandium component or the critical cryogenic treatment process. "They're looking in the right direction but missing the key innovations," Holloway explained to General Curtis LeMay, who had requested her assessment of the intelligence. "They're focused on the chemical composition but haven't recognized the importance of the cryogenic processing. Even if they identified the scandium, they'd need both components of the technology to replicate our results." LeMay, known for his blunt assessment style, nodded appreciatively. "So we maintain our advantage for the foreseeable future?" "At least a year, probably more," Holloway confirmed. "And by then, we'll have further refined the process. We're already working on third-generation variants that show promise for even greater structural integrity with less weight." As 1943 drew to a close, the impact of Holloway's alloy was becoming increasingly apparent in combat statistics. The 56th Fighter Group, flying P-47 seconds equipped with R-41ST components, had established itself as the highest-scoring American fighter unit in the European theater. Led by Colonel Hubert Hub Zemke, the group's pilots had developed tactics specifically designed to exploit the P-47's superior dive capability, approaching enemy formations from above, making high-speed firing passes, then diving away before enemy fighters could effectively respond. This dive-zoom-dive approach, impossible with aircraft lacking the structural integrity to sustain such extreme speed changes, proved devastatingly effective. German pilots began referring to the P-47 as the bomber-destroyer and learned to be extremely cautious when the distinctive silhouette of the Thunderbolt appeared above them. December 1943 brought a formal recognition of Holloway's contribution when she was awarded the Exceptional Civilian Service Award, the highest honor the War Department could bestow on a civilian. The citation specifically mentioned how her metallurgical innovation had provided American fighter aircraft with a decisive structural advantage that has directly contributed to air superiority and reduced combat losses. At the awards ceremony in Washington, Holloway was characteristically modest, directing attention to her team and to the pilots who were putting her alloy to the ultimate test in combat. "The real validation of our work," she said, "isn't in laboratories or test flights, but in the increased survival rates of our aircrews. Every pilot who comes home because his aircraft could dive away from danger represents the true success of this program." As 1944 began, the Allies were preparing for the massive air campaign that would precede the invasion of Europe. The P-47, now produced in ever-increasing numbers and with continuous refinements to Holloway's alloy system, would play a central role in this campaign. The aircraft's combination of firepower, ruggedness, and its unique ability to dive at speeds approaching 600 miles per hour made it particularly effective in the ground attack role, where pilots often had to make steep diving attacks on heavily defended targets, then escape rapidly from anti-aircraft fire. Back at Republic's research laboratory, Elizabeth Holloway and her team were already looking toward the post-war era. They recognized that their wartime innovations in metallurgy would have significant civilian applications once peace returned. The same structural properties that allowed fighter aircraft to withstand extreme aerodynamic stresses would be valuable in commercial aircraft, allowing higher speeds, greater safety margins, and improved fuel efficiency through weight reduction. April 1944, an airfield in southern England. The distinctive rumble of P-47 Thunderbolt engines filled the air as the 56th Fighter Group prepared for another mission over Nazi-occupied Europe. Among the pilots was Lieutenant Michael Brennan, a recent replacement who had yet to score his first aerial victory. As ground crews performed final checks on his aircraft, Brennan ran his hand along the wing's leading edge, a gesture that had become something of a ritual among P-47 pilots. "Treat her, right?" said Master Sergeant Frank Doyle, the crew chief supervising the pre-flight checks. "That wing's special, you know. Some lady scientist back home figured out how to make metal that won't quit on you when you need it most." Brennan nodded. He'd heard the stories during training how the P-47's extraordinary dive capability had saved countless pilots when outnumbered or outmaneuvered. "Hope I don't need to test that today," he replied with a nervous smile. "Better to have it and not need it," Doyle said, patting the wing affectionately, "than need it and not have it." 2 hours later, Brennan found himself in a desperate situation 27,000 feet over Belgium. Separated from his formation during an intense dogfight with Luftwaffe fighters, he faced 3 Focke-Wulf 190 seconds alone. Despite his best defensive maneuvers, the German pilots, clearly veterans, had him bracketed, taking turns making firing passes while he exhausted his energy and altitude trying to evade. With his options dwindling and ammunition nearly depleted, Brennan remembered his training: when all else fails, dive. He rolled inverted and pulled the stick forward, pointing the P-47's nose straight down. The massive fighter responded instantly, gathering speed with breathtaking rapidity. The airspeed indicator swept past 450, then 500, then 550 miles per hour as the ground rushed up with terrifying speed. Behind him, the pursuing Focke-Wulfs attempted to follow but quickly fell back as their airframes began to buffet violently at speeds their structures couldn't safely handle. By the time Brennan finally pulled out of his dive at 10,000 feet, subjecting himself to crushing G-forces that nearly caused him to black out, the German fighters were specks in the distance above him, unable to pursue. When Brennan landed back at base, shaking with adrenaline and relief, he sought out Sergeant Doyle. "You were right about the wings," he said, his voice still unsteady. "I don't think I'd be standing here otherwise." Stories like Brennan's were becoming commonplace across the European theatre, as P-47 pilots repeatedly exploited the structural advantage provided by Holloway's alloy to escape situations that would otherwise have been fatal. What made these escapes particularly remarkable was that they required no special piloting skill beyond the courage to push the aircraft to speeds that conventional wisdom had once declared suicidal. Back in the United States, Elizabeth Holloway was now directing an expanded research program that encompassed not just the R-41S and R-41ST alloys for the P-47, but various specialized derivatives for other aircraft types. The success of her original innovation had earned her considerable autonomy and resources, with both military and corporate leadership recognizing the strategic value of her metallurgical expertise. In May 1944, she received an urgent request from the Pentagon. Intelligence reports indicated that the Germans were working on a new generation of jet-powered fighters that would dramatically outperform existing propeller-driven aircraft. The Messerschmitt Me-262, already in limited production, could reach speeds approaching 540 miles per hour, in level flight faster than any Allied fighter could achieve except in a dive. The question posed to Holloway was stark. Could her alloy technology be adapted to help counter this emerging threat? The P-47, for all its strengths, could not match the Me-262's speed in level flight, regardless of its structural integrity. But perhaps there were other applications for her metallurgical innovations that could help bridge the performance gap until Allied jet fighters could be fielded in significant numbers. Holloway assembled her core team, James Chen, Maria Diaz, and Robert Weissman, for a brainstorming session that would stretch late into the night. They considered various approaches, from enhancing existing fighters to creating specialized intercept aircraft using their advanced alloys to allow extreme performance profiles. The fundamental problem, Holloway explained as she sketched on a blackboard, is that we're reaching the limits of what propeller-driven aircraft can achieve, regardless of structural materials. Aerodynamic drag increases exponentially with speed, and propellers lose efficiency as tip speeds approach the speed of sound. But what about our alloy's weight advantage? Chen suggested. If we can't match the Me-262's speed, perhaps we can create fighters with better acceleration and climb rates by making them significantly lighter while maintaining structural integrity. This insight led to a new direction. Rather than trying to match the Me-262's top speed, they would focus on creating lighter, more agile fighters that could outmaneuver the jet and exploit its weaknesses, particularly its poor acceleration and relatively wide turning radius. The resulting project, codenamed Hummingbird, involved a comprehensive redesign of the P-51 Mustang's wing structure using an ultra-lightweight variant of the R-41S alloy that Holloway's team designated R-41SL Republic 41 Scandium Lightweight. By reducing the weight of key structural components while maintaining their strength, they aimed to improve the P-51's power-to-weight ratio, enhancing its acceleration, climb rate, and maneuverability, all critical factors in countering the Me-262's speed advantage. The technical challenges were substantial. Simply reducing material thickness wouldn't work, as this would compromise structural integrity under stress. Instead, Holloway's team developed a honeycomb internal structure that maintained rigidity while dramatically reducing weight. This approach, combined with the superior strength-to-weight characteristics of the scandium-enhanced alloy, promised to reduce the wing weight by nearly 23% without compromising its load-bearing capacity. By June 1944, as Allied forces stormed the beaches of Normandy, the first prototype P-51s with the R-41SL wing structure were undergoing flight testing at Wright Field. The results were promising. The modified Mustangs showed a 12% improvement in acceleration from 200 to 400 miles per hour and a 15% better climb rate than standard production models. While still not fast enough to catch an Me-262 inches level flight, they had the agility and energy retention to potentially outmaneuver the German jets in the types of turning engagements that characterized air combat. As these tests proceeded, Elizabeth Holloway received unexpected news. Her work had caught the attention of the Manhattan Project, the top-secret program developing atomic weapons. Dr. J. Robert Oppenheimer, the project's scientific director, had requested her consultation on metallurgical challenges related to the implosion design for the plutonium bomb. This request created a difficult dilemma. Holloway's work on aircraft alloys was directly saving lives daily in combat theaters, and the Hummingbird project promised to help counter a significant emerging threat. Yet the Manhattan Project represented a potentially decisive weapon that could end the war entirely. After consultation with General Arnold and senior War Department officials, a compromise was reached. Holloway would remain primarily focused on her aircraft alloy work, but would devote 1 week per month to consulting at Los Alamos on the specialized metallurgical challenges facing the implosion device. This dual role further enhanced her security clearance and expanded her awareness of cutting-edge materials science work across the war effort. It also gave her access to exotic materials and processing techniques being developed for nuclear applications, some of which would eventually find their way back into her aircraft alloy research, creating unexpected synergies between these seemingly disparate fields. August 1944, as Allied forces pushed across France following the breakout from Normandy, the first P-47 seconds equipped with the latest R-41ST alloy components were demonstrating their worth in the intensive ground attack operations that characterized this phase of the campaign. The Thunderbolt's 50 caliber machine guns and capacity to carry bombs or rockets made it a formidable ground attack platform, and its structural integrity allowed pilots to execute steep diving attacks that maximized accuracy while minimizing exposure to anti-aircraft fire. Captain David Allen, commanding a P-47 squadron in the 9th Air Force, wrote in his after-action report following missions supporting Patton's Third Army, "Our ability to attack from high altitude in near-vertical dives, deliver ordnance with precision, and then pull out at extreme G-loads without structural concerns has been instrumental in destroying German armor and transport. Enemy anti-aircraft gunners simply cannot track our aircraft effectively at the speeds we maintain during these diving attacks." The impact on German ground forces was devastating. Field Marshal Gerd von Rundstedt, commanding German forces in the West, noted in a communiqué to Berlin, "Allied fighter bombers have achieved such complete air superiority and operate with such impunity that daylight movement of our forces has become nearly impossible. Particularly effective are the heavy American fighters that attack in near-vertical dives at speeds our anti-aircraft gunners report make tracking impossible." By September 1944, Holloway's metallurgical innovations were having an impact far beyond the P-47. The P-51 Hummingbird program had progressed from prototype to limited production, with the first modified Mustangs reaching fighter groups in England. The F-6F Hellcat, incorporating the N-41S naval variant of her alloy in critical structural components, was dominating Japanese air forces in the Pacific. Even the massive B-29 Superfortress bombers, beginning their strategic campaign against the Japanese home islands, benefited from weight savings and structural integrity enhancements derived from her work. During her monthly visits to Los Alamos, Holloway had developed a professional relationship with Oppenheimer that was based on mutual respect and a shared understanding of how materials science underpinned much of the war's technological race. During one such visit in October 1944, after reviewing her contributions to the implosion lens design, Oppenheimer made an observation that captured the unique nature of her work. "You know, Dr. Holloway," he said, looking out over the New Mexico desert from the laboratory window, "what we're creating here may end the war, but it's a weapon of last resort, something we hope never to use again. Your work, on the other hand, is saving lives every day in the skies over Europe and the Pacific. There's something profoundly different about innovation that protects rather than destroys." Holloway nodded thoughtfully. "The irony is that my alloys make aircraft more effective weapons platforms, but they also bring pilots home when they'd otherwise be lost. It's that dual nature of wartime innovation that I find most complex, how the same technology that increases lethality can simultaneously be protective." This philosophical exchange reflected Holloway's growing awareness of the moral complexities of her work as the war progressed toward its conclusion. She had entered the field of metallurgy with a passion for scientific discovery, never anticipated that her research would become so directly entwined with the life and death struggles of combat pilots half a world away. By early 1945, as Allied forces pushed into Germany from both east and west, the full impact of Holloway's metallurgical innovations was becoming apparent in combat statistics. The 56th Fighter Group, flying P-47 seconds throughout their combat tour in Europe, had established itself as the highest-scoring American fighter unit against German aircraft, with 677 confirmed aerial victories. More telling than these offensive statistics was their loss rate significantly lower than comparable units flying aircraft without the structural advantages provided by the R-41S alloy family. Colonel Hubert Zemke, who had commanded the 56th for much of its combat tour, specifically credited the P-47's dive capability with saving countless pilots. When all other tactical options are exhausted, our pilots know they have one final card to play a dive at speeds no enemy aircraft can match without structural failure. This knowledge not only saves lives directly, but enhances overall combat effectiveness by giving pilots the confidence to engage aggressively, knowing they have a reliable escape option if the situation deteriorates. In the Pacific Theater, as American forces advanced through the Philippines toward Japan, the P-47 Newtons variant, a long-range version with strengthened wings for carrying additional fuel tanks, was proving particularly effective against Japanese fighters. The structural integrity provided by the latest R-41ST alloy allowed P-47 Newtons pilots to use their aircraft's weight and diving power to literally tear through formations of the more lightly built Japanese fighters, then escape at speeds the Japanese could not match. Marine Captain James Coleman, flying P-47Ns from bases in the newly recaptured Philippines, reported after a particularly intense engagement, "Our ability to dive at over 550 miles per hour when necessary completely confounds the Japanese pilots. Their aircraft simply cannot follow without coming apart, and they know it. This creates a psychological advantage as significant as the technical one they hesitate to pursue when we dive away, giving us control of when and where to engage." As the European War reached its final stages in spring 1945, Elizabeth Holloway received an unusual request. General Jimmy Doolittle, commanding the 8th Air Force, asked her to visit England to receive first-hand recognition from the pilots whose lives her work had saved. Despite her reluctance to leave her research at a critical juncture, she recognized the importance of connecting directly with the operational realities of her innovation. The visit, in April 1945, as Germany teetered on the edge of defeat, proved profoundly moving. At airfields across eastern England, Holloway met pilots who had survived seemingly hopeless situations because their aircraft could structurally handle maneuvers that would have torn other fighters apart. Many had no idea that their survival had hinged on the work of a female metallurgist, a rarity in the male-dominated engineering world of the 1942nd. At the 56th Fighter Group's base, a ceremony was held where pilots who had used the P-47's exceptional dive capability to escape certain death or capture came forward to shake Holloway's hand and share their stories. The event, initially planned as a brief formal recognition, evolved into hours of emotional personal accounts, as pilot after pilot described moments when the structural integrity of their aircraft had meant the difference between life and death. Captain Michael Brennan, who had survived the encounter with 3 Focke-Wulfs the previous year, approached Holloway with tears in his eyes. "Dr. Holloway," he said, his voice breaking slightly, "I have a wife and a daughter. I've never seen she was born while I was overseas. Because of what you did, I'm going to go home and meet her. There's no adequate way to thank you for that." Similar scenes played out at other fighter bases, with pilots lining up to express their gratitude. By the end of her 2-week tour, Holloway had met over 100 airmen who credited their survival directly to the structural capabilities her alloy had provided. The technical achievement that had begun as an abstract metallurgical challenge had transformed into something profoundly human, a direct connection to lives preserved and futures restored. Upon her return to the United States, Holloway found herself increasingly thinking about the post-war applications of her work. The R-41S alloy family had proven its worth in the extreme conditions of combat, but its potential extended far beyond military aircraft. As victory in Europe arrived in May 1945, followed by Japan's surrender in August after the atomic bombings of Hiroshima and Nagasaki, the question of how to transition wartime innovations to peaceful purposes became increasingly urgent. In September 1945, with the war finally over, Holloway presented a comprehensive proposal to Republic Aviation's leadership, outlining how their exclusive rights to the R-41S alloy technology could position the company advantageously for the anticipated post-war aviation boom. Her vision extended beyond military contracts to the emerging commercial aviation market, where the alloy's combination of strength and lightweight would translate directly to improved safety, performance, and efficiency. The same properties that allowed a P-47 to dive at 550 miles per hour and pull out safely will enable commercial aircraft to withstand unexpected turbulence and aerodynamic stresses with greater margins of safety, she explained to Republic's board of directors. And the weight savings will translate directly to increased payload capacity and fuel efficiency, both critical factors in the economics of air transport. Republic's leadership embraced this vision, establishing a new commercial materials division with Holloway as its director. The first major application came quickly, as American airlines began expanding their fleets to meet surging post-war demand for air travel. The Convair 240, one of the first modern airliners to enter service after the war, incorporated Holloway's alloy technology in its wing spars and other critical structural components, allowing a lighter yet stronger airframe than would otherwise have been possible. The legacy of Holloway's wartime innovation extended far beyond these immediate applications. The fundamental approach she had pioneered using trace amounts of scandium combined with cryogenic treatment to dramatically alter the microstructural properties of aluminum alloys became a cornerstone of modern materials, science, applicable to everything from jet aircraft to spacecraft. When the sound barrier was broken by Chuck Yeager in the Bell Zone in October 1947, the aircraft incorporated structural elements derived directly from Holloway's work. The extreme aerodynamic stresses encountered at transonic speeds required precisely the kind of structural integrity her alloy technology provided. As Yeager famously remarked after his historic flight, the real question wasn't whether I could fly the X-1 past Mach 1, it was whether the aircraft would hold together when I did. Thanks to some pretty remarkable engineering in the structure, it did. By the early 1952s, virtually every American aircraft, military or civilian, incorporated some version of the scandium-enhanced alloys that Holloway had pioneered. The technology had become so fundamental to aviation that it was easy to forget how recently it had been considered impossible or impractical by the metallurgical establishment. In 1952, Elizabeth Holloway was awarded the National Medal of Science for her contributions to materials science and aviation safety. The citation specifically mentioned how her wartime innovations had not only contributed materially to Allied victory, but established new paradigms in metallurgy that continue to enhance aviation safety and performance in peacetime applications. At the White House ceremony, President Truman, who had authorized the use of the atomic bombs that ended the Pacific War, made a poignant observation. Dr. Holloway's work represents the finest tradition of American innovation, creating technology that saved lives both during war and after. While some scientific breakthroughs are remembered for their destructive power, hers will be remembered for how many people survived because of it. Perhaps the most meaningful recognition came in 1955, when the Air Force Association established the Holloway Medal for Aeronautical Innovation, an award specifically recognizing technical contributions that enhanced aircraft safety and survivability. The inaugural presentation was made by General Jimmy Doolittle, who had arranged her visit to England a decade earlier. Dr. Holloway's contribution reminds us that the most significant innovations are often invisible to the casual observer, Doolittle noted in his presentation speech. A stronger, lighter alloy doesn't capture public imagination like a bigger engine or a sleeker design. Yet nothing is more fundamental to aviation progress and safety than the materials from which aircraft are constructed. Her insight transformed not just what aircraft could do, but what pilots could survive. Elizabeth Holloway continued her research throughout the 1,950 seconds and into the 1,960 seconds, developing new variations of her alloy technology for the jet age and eventually for the space program. When the first American satellites and later the Mercury, Gemini, and Apollo spacecraft were designed, her metallurgical expertise contributed to structures that could withstand the extreme conditions of launch, orbit, re-entry, and splashdown. Her legacy extended beyond her direct technical contributions. Through the generations of scientists and engineers she mentored, many of them women who found in her an example of what was possible in fields traditionally dominated by men. Maria Diaz, who had been part of her original wartime team, went on to establish the Materials Science Department at MIT, bringing Holloway's practical, problem-solving approach to metallurgy into the academic mainstream. The ultimate testament to Holloway's impact came not from medals or academic recognition, but from the countless lives influenced by her work pilots, who returned home when their aircraft withstood stresses that would have destroyed conventional designs, passengers who survived severe turbulence or weather because commercial airliners incorporated her strengthened alloys, astronauts who safely re-entered Earth's atmosphere protected by spacecraft structures derived from her innovations. At her retirement ceremony in 1968, a surprise guest appeared retired Captain Michael Brennan, the P-47 pilot who had thanked her in England for allowing him to return home to meet his infant daughter. Now a commercial airline pilot, Brennan arrived with that daughter, now a poised young woman studying engineering in college. "Dr. Holloway," he said, his voice thick with emotion, "I want you to meet Catherine. She's studying materials science because of the stories I told her about a brilliant woman whose work in metals saved her father's life before she was even born. Your legacy isn't just in aircraft, it's in the generations who would never have existed without your innovation." As Elizabeth Holloway looked at the young woman whose very existence was, in some sense, a consequence of her work decades earlier, she understood the true meaning of innovation, not abstract technical achievement, but the profoundly human impact of solutions to seemingly insurmountable problems. The metallurgical establishment said it was impossible, she reflected in her final interview, given shortly before her death in 1985. They said no aluminum alloy could withstand those stresses without becoming too heavy to be practical. But science progresses when we question these certainties, when we ask not just what is known to be possible, but what might be possible if we approach problems from an entirely new direction. The P-47 Thunderbolt, armed with Holloway's revolutionary alloy, had given American pilots the ability to dive at 550 miles per hour and survive a capability that had saved countless lives and contributed to Allied air superiority. But its greater legacy was in demonstrating how a single innovation, born from questioning established limitations, could cascade through technology and time, creating possibilities that extend far beyond its original application. That legacy continues today, in every aircraft that flies higher, faster, and safer, because one metallurgist refused to accept impossible as the final word. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell, so you don't miss any upload from us.